fairly regularly because I'm the chairman. Moving on, interesting topic this evening, general artificial intelligence. We're going to talk about what it is, how it works, maybe, and what people are doing in the area right now, and some recurring themes you see. So first, defining artificial intelligence. One thing that's bandied about a lot is called the Turing test. The Turing test is this idea of, okay, you can have an actual, true, general human level intelligence if you can stick it in a room with a tester and have them talking through a teletype interface where they're basically IMing back and forth, and the person on the other side legitimately can't tell whether it's a human or an AI, which is great. That would probably tell one way or another if something was intelligent, except for a few problems. One, people have been fooled before by programs that pretend to be 13-year-olds, because 13-year-olds don't know that much, and in general, apologies to any 13-year-olds that were offended by that statement. My apologies. But in general, they can be sort of weird and no one really notices because it's a child. You expect them to do things differently sometimes. However, the comparison's been made, and I really like this one, with aeronautical engineering tests do not define the goal of their field as to making machines that fly so exactly like pigeons that they can fool other pigeons. It's not really the most useful metric for evaluating how general AI is. So, a more interesting and perhaps relevant criteria is Bentham's felicial calculus, which is basically you want to maximize pleasure and minimize pain. So, my favorite sort of toy way to evaluate how well an AI is doing is to have a library of games, not just one game. There's lots of AIs that have been written that can beat one game, but have thousands of games. And the AI tries each of those games, and if it does well at all of those games, you can say, hey, that's a general AI, because a human can learn to play more than one game. So, going forward from there, the trick with that is you need to define what is the AI considers to be a good thing versus a bad thing. In a game, it's pretty straightforward. You want to win the game and rack up as many points as possible. For an actual general artificial intelligence that's supposed to do all sorts of crazy things and maybe get smarter than a person, that's really complicated. I'll talk about singularity stuff in a little while, but a good example that I've heard and is bandied about is, well, a good AI wants to make people happy, so they try and make people smile, right? That's a good way to see whether it's a nice AI, a helpful AI. Well, it's been pointed out that one way that you can make everyone smile is to release a virus into the world that locks everyone's jaws like this. And that would probably be easier than trying to make everyone in the world happy. But not really the goal that you want. So this is actually an important and very active field of research in general AI right now, with big names like Elon Musk pledging, I think it's at least $1 billion toward a non-profit to try and research, okay, how can we define a goal function so that if our AI gets smarter than us, it's still nice and friendly and does things that we want. So, important names, big names. Why is this really important? The concept of singularity. Specifically, this big thing that was in 1965 boils down to, well, gee, if we make an AI that is as smart or smarter than a guy, then maybe it could design another AI or an extension to itself that would make it even smarter. And then after it gets that upgrade, it gets smarter and can build a better one because it's smarter, so it just recursively makes itself more and more smart until it's more brilliant than the entire human population of the Earth and can do pretty much whatever it wants. There's a lot of programmers in the audience tonight. I think we appreciate that having raw intelligence can be pretty darn handy, and there's a lot you can do with it. An analogy for things that a singularity AI could do that's been made a few times is, okay, what if you had the entire nation of the United States in this little virtual box, and all we could do is communicate by typing out. If you had, and let's say their time was sped up, so that for each year in the outside world, or for each second in the outside world, it was a year in the United States. We would have papers, we would have conferences, there would be all sorts of things that we do to say, okay, this is what we should say next. And can you imagine the sheer novelty that, I mean, Pixar films, for instance, that's something that you could just export over a digital connection, no problem. There's lots of things that a super intelligent thing, even restricted to a computer, could do. It's been said, I had trouble tracking down the exact quote, but we're building a demigod. What could possibly go wrong with that? Because the idea is something like this. I mean, we've all seen Terminator. It could build its own industrial complex, and there's not really a limit to what a super intelligent something could do. So it's really important you do it right, because there's another principle that apparently I didn't stick on the slide called winner take all. The idea is if you build an AI that's super intelligent, the first thing it will do is immediately find any other super intelligent AIs that are coming online and immediately shut them down. Because it only has one goal function, one thing that it considers the most important thing in the world to do. And any other super intelligent agent would be potentially not have the same goal function, so it would make sense for it to immediately calm that down, shut it down, that sort of thing. So, I've talked a reasonable amount. Are there any questions, or should I move on? We are on the same page with singularity, could be a big deal. Cool. So, defining formally, I think you can define a artificial intelligence, a general artificial intelligence, as a reinforcement learning agent. So specifically, you can define it as a function where it can take actions in response to perceptions that gets in. So, do they have chalk around here? They have whiteboard markers on a blackboard. Okay.
There's some chalk at the end.
Ah, good. There's some here too. So, let's think of this as like a turn-based game, because anything can be broken down into a turn-based game if you have small enough time slices. So we have our black box AI. We have our black box AI. And at each step of the game, come in?
I said it's a blue box. Sorry, go ahead.
It is a blue box. That is not true. At each step of the game, it gets some sort of information about the outside world. Some sort of sensor information, something like that. That gets in. It also gets some sort of reward signal, R. That goes in. And then at each step of the game, it gets to take some action A. And these are all defined as numeric inputs. So this is a bunch of numbers. This is one number that says, hey, you did well, or no, you're suffering terribly. Yes?
Blue is hard to see back here.
All right. All right, we have some white box. So, we have some function that potentially playing the game multiple times or just living a really long time. It gets perceptions in, it gets some sort of reward at some point in time for something it did, maybe, or pain, and then it tries to take actions to try and maximize that reward. Basically, it's playing, this is what it sees on the screen, this is its points, this is what it does with the controller. Basic game. But the nice thing is, this can be an arbitrary dimension, this could be an image, this could be a video, it could be all sorts of different things. The reward function, we're going to for now say this is an external function that says, hey, you won the game, or you just racked up a bunch of points. Because we're talking that general game playing AI. And then this is whatever actions are possible And if there are actions that are possible in some states and not possible in others, you could define it so it gets punished whenever it does an action that isn't possible, and it just loses points. And then it would hopefully learn to avoid doing that. So is the idea of this is the function, what reinforcement learning is, does that make sense? Reasonably clear? Cool. So, we talk a lot about supervised learning. You hear a lot about with it machine learning in general, particularly neural networks recently. There's a lot of mystery around it, I feel. It's not necessarily clear how it all works. This is it, pretty much. You have some function, call it f of x. It's a function. It takes an input, it gets an output. You have examples of that f of x. Say f0, f10, whatever. Just points, examples of its output. You have the input, you have the output. You want to make some function, f star, that approximates as well as possible this unknown function f. Does that make sense? You're just trying to make a function approximator. That's all supervised learning is. Those functions could be discrete, in which case you have a classifier, or they could be continuous, in which case you have something that does regression. But all it boils down to is you're trying to make a function approximator. So, I'm going to assume, moving forward, that you have some sort of function approximator. It's not necessarily optimal, but hopefully it's good enough, and let's see what we can do using that. So, there's something called Q-learning. It is a reinforcement learning technique, so it tries to solve this game playing problem, and what it says is that you should try and use a supervised learning method to predict for any given state how well that's going to work out for you. So let's say I'm playing chess. I have a certain number of moves available to me. What it's trying to answer is, if I make this move, I think it's going to work out this well, given me. Now this is a bit more of a leap than the other ideas. But let's say I'm standing on a bridge, and in front of me there is a piece of cake, and there is a unguarded railing where I could jump off. I'm looking at the piece of cake and the unguarded railing. I see two options available to me. I could eat the piece of cake, or I could jump off the bridge. I'm making an evaluation saying, I think eating that piece of cake could be really nice and work out well for me. And I think jumping off the bridge, that's a terrible idea. That's a Q function evaluation. My state is I'm on the bridge and I see cake and a way to jump off the bridge. And what I'm trying to evaluate is, given the rest of the future, this is how well I think it'll eventually work out. So moving that back to the game parlance, what they do is they take the net present value at the end of the game and they propagate it back to try and figure out what the Q value would have been. Okay? So, raise your hand if you're familiar with net present value. Okay, enough that's good to go over a little bit. So, who here has heard of compound interest? Pretty much everybody. So the idea is, in reinforcement learning, there's this issue of, I can do an action here that gives me a reward, but that reward doesn't happen until way over here. So how on earth can I tell this had anything to do with that? Well, the idea is, on average, if I play this game a lot, if I do this, eventually, on average, I will get more reward for doing this action than I would for not doing this action, given how I tend to play the rest of the game. So what they do is they say, okay, let's take our turns here, and whenever we get a reward that happens, or pain or whatever, what we'll do is we'll propagate this back and say, okay, if my discount function is, say, 0.1, then here I will give that a reward of 1, here I'll give a reward of 0.9, and then I think it's 0.81, and then I don't care to do the rest of the math there. But you guys get the idea. You just multiply it by the discounting factor each time. So 1 minus 0.1 is 0.9. And then as it goes back, eventually you'll get a whole bunch of things saying, okay, this guy tends to work out well. Because there's a lot of different futures that I can go throughout here, but most of the ones where I don't jump off the bridge turn out okay. Does that seem reasonable? So the cool thing is, this converts our reinforcement learning problem from something that's really hard, this reinforcement learning thing, to a supervised learning function. Which, as we said before, we're assuming that there's potentially some good supervised learning function that we can use. So, Q function. Q learning, it's an interesting thing that is used in many different applications, including AlphaGo, which is a recent thing that is in the news and all over the place. There's also some cool things that you can do with Q learning. In particular, this whole idea here is saying, okay, given my state, this is how I think things are going to work out, given how I tend to play things in the future. Well, maybe if I'm trying to estimate this Q function, where it's literally just state here as your input, to if I state and action to this is how much reward I think, this is how well I think it's going to pan out with that. What you can do is take a game player that's not you, that isn't your AI, that's a normal person playing StarCraft or something like that, and you can feed what they did. At each action where they win the game, you can propagate back their Q values and then feed it to the AI, and whenever it sees that similar situation, if it has a good supervised learning function, it can say, hey, I remember when Jaedong played this game, he was in a similar situation and he did this, and it worked out awesome. Which is great because one of the things that's really hard for reinforcement learning AI that's just playing the game is to figure out stuff like, oh, to select my units, I right-click here and then drag across and then hit left-click. That's something you generally wouldn't do if you're just doing random motions because you have no idea what these numbers mean. But if you're watching someone that's playing the game, you figure out, oh, that's how the mouse works. And then you can potentially learn a lot more by playing the game yourself. So some cool stuff if you take this Q learning approach. However, there's a problem with doing just pure Q learning, which you can illustrate with something called the in-armed bandit problem. So the in-armed bandit is just slot machines. Literally, there's a whole bunch of slot machines. Each one has one arm that you can pull back. You just pull it down, and you have a certain probability of getting a reward, and the reward's going to be a certain amount. So, lots of slot machines. The big question is, you have no idea what the reward associated with that machine is, or what the probability of success is going to be. You could just go through and pull on the slot machines until you get a single reward and then say, aha! I found one that gave me a reward. Therefore, my Q value of pulling this lever is higher than any of the other Q values. So obviously, I should just pull that lever because it has the highest Q value. See any problems with that? You may not have pulled the right lever. There may be another level which gives you a huge reward every time you pull it, but you haven't explored enough. You're cutting out too early. So, this is the problem with the in-armed bandit and the sort of fundamental problem of exploration versus exploitation. It's never really clear how much you should explore. There's always something more you could potentially learn. So, one way to address it that I've been looking at, and I'm not sure if it's in the literature or not, but I've been thinking about it, is called the surprise function. It's similar to Q-learning in that it just takes in your state, history, and whatever your last reward was, and then gives you some, I think if you do this action, it'll work out this well. But rather than training on the net present value in the past games of what it did, instead it's training on, in that last game where you had your Q function, how badly did it mess up? Did you think it was going to be like a wonderful chocolate cake, but instead you fell off the bridge? If so, well, it's not the best example, but maybe you should try that again and see whether you fall off the bridge the second time. But it's the idea of, okay, if my Q function is working well in that space, then I don't really need to explore it all that much. I have a pretty good idea of what's going on in that area. If I'm utterly surprised and gobsmacked, then I guess I don't really know what's going on there. And so hopefully you can have a trade-off where you give your agent, at each action, it has its Q value and it has its surprise value, and it does some sort of weighing function. You say 0.2 surprise and 0.8 Q value, and we'll evaluate the actions based on how much we think they're going to surprise us and how much reward we think we're going to get from it. Because the idea is, with something like a maze, at the start you want to try everything, but eventually the fact that that's a dead end will no longer surprise you, and you'll stop exploring that because, hey, it's a dead end every single time. So in those sorts of stack situations, it should eventually mellow out, and eventually you'll say, okay, I've got this place locked down, it's understood, I'll go and just do pure Q learning. So hopefully I think this could be useful. However, it does have some problems. One, there could be actions that just end the game. In particular, I'm really curious about what suicide feels like. Intrinsically, there's nothing in that formula to say, you really shouldn't do that because it might end the game. One could say that the fact that humans do suicide at all might be part of the whole, we maybe don't anticipate that enough. But that's philosophy and I don't really know. One could hypothesize that we associate pain with anything that could potentially kill us, and we also have our stern parental figure saying, no, don't do that, you scared me half to death. And since part of our goal function is tied to our close people's happiness, we don't want to do that. Just a random thought, nothing really there. The other thing is, they might have a bit of a gambling problem, because they're often they can calculate their Q function, their expected reward for a given action, but if it's really truly random, like there is no pattern there, they will keep on being surprised by it, which means they'll be like, oh, well, I know the reward's a little bit lower there, but everything else being equal, I want to do the surprising thing, which may not be optimal in the long run. So, does that make sense? Cool. So, designing general artificial intelligences. Historically, there have been many attempts at doing this. So far, we don't have a singularity AI that I know of. I think that maybe potential reasons for why things have been so unsuccessful is, one, we haven't had really good supervised learning methods to date. I think we're starting to get there, particularly with deep learning. Two, there are 1,000 different people with 1,000 different proposals on how to get general AI, and none of them have a way to test their proposal. Instead, they just say, yes, this is the ultimate way to get general AI, and maybe I can build it in 20 years. Not really any good testable stuff there. I also think that modularity could be really useful in that you have this general framework and people can swap out different parts, which is one of the reasons why I define, hey, this is supervised learning. It could be any supervised learning method, but it has some sort of function approximator, and the better it works, the better your agent will work. And that allows you to make relatively simple architectures that still have somewhat provable properties. So, this is design number 1 for our general AI. I am not a super AI professor, but this is my crack at it. Oops. I'm not quite there yet. So, this agent is pretty much what we discussed. It has the Q evaluator, or it calculates that Q function. It has the surprise function, which has that whole, how interesting is this area going to be? So, it's pretty simple. We take the current turn of the game, see what happens, and then for our history, we just have a finite memory where we grab every single thing and every single action we've taken and every single reward, and we throw it in there, like a sliding window. And then that is the input to our Q evaluator and our surprise function. And then for each possible action that we can take in that game, which for something like chess isn't necessarily that hard because there's only so many moves you can make, We look at the Q value and we take the one that maximizes that Q value in surprise function, and we take the one that maximizes that weighted sum. Does that make sense in terms of something you could do? Big problem with this is it's completely uncomputable. As you see right up there, where you're taking that huge finite memory, that's a gigantic input to a machine learning function, a supervised learning function. In general, as the dimensionality goes up, it gets harder and harder to do things. So, let's see if we can make that any better in something that's more computable and testable. So, design number 2. You need something that has a compressed memory. You need to look across all of these different experiences and figure out some way to summarize. Because it doesn't really matter how smart you are, your brain is only so big and you can only store so much data. Same with computers. If you're going to have an agent that plays for a really long time, or even just has something that's computable, you need some way of compressing its life story for this particular game run. So otherwise, pretty much the same. Does that make sense? Does that seem reasonable? Alright. Number 3 gets things a little bit more general in that there are types of games where you can't enumerate all your possible actions. In particular, you can have continuous outputs, right? Which have potentially infinite or close to infinite different actions that are possible to take. For instance, when you're piloting a quad rotor, you can do lots of different levels of thrust. It becomes infeasible to try and enumerate all of those different actions. So what you can do is try and define another machine learning function, and rather than doing all of the different possible actions, what it does is it tries to suggest what it thinks will be the maximum, most optimal function of all of these. It tries to guess at the argmax. So in this case, you have something that generates in actions, and it feeds them into the Q evaluator, and then you take the argmax of that. But this is, again, just a supervised learning function with one complication. If you're only feeding in actions, how on earth are you going to tell what's actually the maximum given our Q function? Well, as it turns out, you need to do optimization. Because the cool thing here is, to figure this out, you don't need any outside information. You don't need to know how the game goes. You don't need to know what the actual Q function is. You don't need to know what the Q value for any given action is going to be. What you need to know is, what does this guy think the Q value, maximum Q value is? So you can do any sort of normal function optimization, such as gradient descent, to try and figure out, okay, what's the argmax of this function? Now, you could say, well, then why do you need to do the inaction evaluator at all? Because then you could just do the optimization every time. Fact is, the optimization is really computationally heavy, so you want to do it when you're training, but not when you're out in the field operating. And you can further augment it by doing this inaction thing, where you generate a certain number of actions and then punish based on whether or not the first one is in fact true optimal or close to it, or whether or not the ordering is wrong. Whether the second or the third action is in the order it's supposed to be. You can punish based on that. Yes?
This is basically mathematical modeling.
Which part? Yes. I mean,
that's a compression, right? So you can't, the whole idea of mathematical modeling is because you can't do all the calculations.
Yes.
Right? So they try to create a model which represents the reality that they're trying to represent.
Which is exactly what this guy here is.
Right.
Yes. I mean, what it boils down to, this whole thing can be defined as a set of functions. That's the main gist of what I'm trying to demonstrate here. For years, there's been argument over whether general AI is possible at all. I would advocate that's not just possible, but we're getting toward being able to do it. I don't know how far off it is, but it seems like there's architectures that have provable properties in ways that we can test these. So this is my stab at it so far. So, does this seem relatively clear? Cool. So that's pretty much all of the main stuff. I promised a short talk. I have bonus material I can talk about, including a fun diagram on memory compression, but I promised a short talk, so raise your hand if you want me to keep talking, and otherwise I will stop.
I want to see the memory compression.
Okay.
Yeah.
I think there's at least a simple majority, so we will keep going. So, memory compression.
Charles?
Kind of back to your diagram, so, someone I was recently talking, you said that Amazon's working on AI. Are they working on a similar concept? Or how would what you're working on differ, if you're familiar with their system, like I am not, I think it's a look into it.
Yes.
I figured maybe you may have heard of it.
To be honest, there's an enormous body of research, so I'm familiar with some of the general trends, but I would not consider myself an extreme expert in the
Okay.
field. This is my work so far. I mean, Reed and I were having a discussion just this afternoon about some of the problems with the surprise function, in particular the gambling thing.
But I think they're also selling data, right, from different sets that they have from the customers?
That's kind of scary.
Or
In general, there's a lot of data sets available, particularly for supervised learning. One of the things I've discussed in some of our previous meetings is making a game library to evaluate exactly this sort of agent, and then trying to build some of these agents to try and solve those. So, it's an active field. Stuff like AlphaGo, they're making progress. It's similar in many respects to some of the stuff we're talking about. Yes?
What implementation steps, if any, at this point?
For me in particular,
Sure.
I'm currently working with the Cafe library.
Okay.
And I haven't implemented anything in particular yet. You'll notice that we're working from a theoretical standpoint with the idea being practical demonstrations from there. So we're going to start with simple stuff like mazes and tic-tac-toe, and then go from there.
What big reason for using Cafe? I mean, Adhiano is similar, you know.
I'm a professional C++ developer,
Okay.
so I prefer a C++ library. That's the main reason.
Sure. I mean, in terms of functionality, I mean, Cafe was mainly built for convolutional nets, right?
Mm-hmm.
What types of nets have you been building with it?
Not too much yet.
Okay.
I've mostly been working with a library called tiny_CNN recently, and I've been switching over to Cafe now.
Okay.
So
Like
you
I said-
load the tic-tac-toe results into your system, or have it play the game?
Yeah, so what you do is you have it play the game, and hopefully it would do stuff like intelligently explore all the different ways to win tic-tac-toe, because it can exhaustively explore it. You could also give it a tic-tac-toe opponent that plays perfectly and see how it does against that. In fact, it'd be interesting to see whether or not you could have it automatically look at the opponent's position in a game like that where you have total position, total state information, and see whether it could learn based on that. Oh, that worked out really well for the enemy. The problem is there you don't really know the enemy's true state because you don't know if you have perfect observability of the environment. But like I said, these models are general enough that you have a function approximator. Let's see if this will work just from basic logic for now.
And you might be interested in looking up something called deep Q-learning or Google's Atari solver, which uses something very similar to this and learns how to play Atari games.
Using the convolutional layer as the base stuff. So, memory compression. If I asked you to summarize in 3 words your last minute, what would you say?
Charlie Talk.
Charlie talk a lot. Maybe chair uncomfy or something like that. Yes, reasonable. So one of the key insights that they had in convolutional neural networks, in particular for image processing, is why on earth should I treat one patch of pixels any different than I treat any other patch of pixels? Why can't I learn a filter that then I apply to all of those pixel patches rather than just saying, this pixel over here I think is super significant for classifying this image. Instead, you treat all of them the same and do filters, transformations on them, and then learn the ideal filter. So this is sort of applying the same idea to those games we were talking about. You have your perceptions, reactions, and rewards. Call them these little blobs here. So the idea is, I want to do a autoencoder, and I can get into autoencoders in a second, that summarizes my whole life up into this finite state array. So each of these pink guys, I guess, as it turned out. I was aiming more of a red, but I guess it came out pink. It compresses, say, a minute. And then each of these guys try and compress your minutes into, well, if my diagram was bigger, hours. And then each of those hour compressions try to compress up to days, and days to years, and so on and so on. So how that looks and how that works, raise your hand if you've heard of an autoencoder. Okay, so low enough that I should explain it. So the idea with the autoencoder is that you don't necessarily know the best way to compress your data. But you have lots of data, and the data has some regularities in it, but you need to figure out what. So what we want to do is have one input layer for a neural network that is our data. Say this is image. And we want to shrink this down to something that has lower dimensionality. Let's say 128 characters to describe this whole big image that has millions of pixels. So what we do is we have this weird looking neural network called an autoencoder. And what it does is here it has connections. But the connections are the size of that compression output that we want. Here, we have connections that go to all of the pixels in the image, learning different stuff about it. Here, we have connections that go from that little condensed summary to the image. And the idea is what this neural network is trying to learn how to do is take this image, compress it down to this little tiny summary, and then reconstruct the original image with maximum fidelity, given the fact that it can only pass through a little bit of information through this bottleneck. And that's called an autoencoder. The cool thing about autoencoders is you don't need labeled data to be able to do it. You can just have it go through all of these different images and try and learn stuff like edge detectors, where it can detect, hey, there's an edge here, and at higher levels, stuff like eye detectors. And then face detectors, because whether or not there's a person there is actually pretty important in terms of reconstructing the whole image. So the idea is, since it can only remember a little bit, it remembers the important stuff, because that matters the most for reconstructing it. So what we're doing here is applying the same idea to the experiences in the game, where we're having it, at this layer, try and learn some way of compressing, let's say, 10 seconds into this little tiny feature vector. And then we're trying to make another layer that compresses a bunch of those little tiny feature vectors into a smaller set than the combination of all those vectors. And on and on and on until we get to this compressed summary here. And then once we finally get to the end, once this whole thing is trained after the recordings of many different games, what we do is we chop off the top part of the network and say, this is our summary right there, that bit in the middle. And that's what we feed into our Q-learning AI. There's also an optimization you can do where after you have some pre-training, you can actually hook it into your Q-learning function and take the backpropagation gradient off of that to learn information that's relevant to deciding your Q function. But that's slightly more involved.
Charlie, do you keep the reconstructor part, or do you make the...
Only if you're training your reconstructor more. If all you're doing is actually using the compressions rather than trying to learn the compressions as you're going, you throw away the reconstructor and just use the summary as your input to the whatever other neural network you're working with. So for image classification, for example, they would do stuff like using these stacked autoencoders or denoising autoencoders, which are a little different. And they would pre-train on a whole bunch of unlabeled images. I mean, they'd just search through Google and grab as many images as they could. And then, once it had done all that pre-training, they chop it off and say, okay, you're part of our network now, so learn stuff that's relevant to our particular data set and trying to decide whether or not that's a cat. Does that make sense?
It just seems that the thing that's going to be using this compressed chunk in the middle is going to have to not only learn what it means, but also learn how to reconstruct it.
Well, it doesn't have to reconstruct the whole thing to decide whether or not it's a cat.
Yeah.
So it may just decide, oh, that one piece over here, this one output, is whether or not there's a cat in the image, because that's important for reconstructing it. In fact, Google Brain was somewhat famous for naturally figuring out where cats were in the image, because apparently that was really important for internet images for some reason.
So one question,
Mm-hmm.
you have some new and improved experiences, how hard is it to update that compressed version?
Well, if you tie it into your queue function, that may happen automatically. In fact, you may be able to even skip the autoencoder style learning and just have it do tie back to the queue function. So, but that is getting away from the just function approximator thing and going into the particulars of neural networks, like being able to propagate back the error. So, master-apprentice reinforcement learning is an idea that I haven't extensively checked the literature on, but seems very feasible, and I came up with, what was it, last week? Week before? Okay, so the general idea is you have a lot of games where it's very, very hard for an AI that's just doing random stuff to figure it out. Like, for instance, if you're playing Quake, it may take you a really long time to figure out it's not just random happenstance I get hit with a rocket, it's because I'm not dodging, that sort of thing. If you're just randomly spastically moving in one area, you're never going to figure that out. You'll just die every time. So, the idea is anyone familiar at all with Renaissance painters?
What?
Renaissance painters? One thing that the great masters did with their apprentices back in the Renaissance, what they had was that they had them slavishly copy the works of the great masters. They would set the painting down and then have them recreate it as exactly as they possibly could so that they could learn, hey, what's important in drawing something like this. The idea is similar here. There are many domains where it's possible to build a simple agent that plays the game. Not well, but okay. Not very good, but okay. For instance, with the online game Dota, they have AIs for like 7 different heroes, and they play all right in that they have perfect timing on some stuff. There's some things that AIs are just intrinsically really good at, but in terms of the Gradle strategy, as far as knowing where to be, when to be, what to do, they're terrible at it. They can do the basics of the game, but they're really, really bad at the higher level play. So, what I propose with this master-apprentice model is that what you do is you design a master AI, which is one of these simple AIs that can play the game okay. Not great, but okay. And before you have the apprentice, which is your reinforcement learning AI, actually try and play the game, rather than having it just spastically try and run around and figure out what it's doing, instead, you train it so that whenever it does exactly the same thing as the master AI in a given situation, it gets a reward immediately. No propagation, no weirdness, it just immediately says, yay, I'm happy, that's great. You can also import the Q values, which is a somewhat more direct way of doing this. So what the reinforcement learning AI learns to do in this instance is play the game exactly like the okay/crappy AI. It learns to, in the instance of Dota, attack the enemy. That's an important thing to do. Go attack neutral creeps to make money, that sort of thing. It doesn't have a sense of the high-level play, but one could argue that if you completely train it on this master AI, it will learn to play the game without ever using any keyboards, keystrokes, or anything. It will learn to play the game about the same as your master AI. No worse. However, once it reaches that level of capability, you can switch off the whole following the master AI slavishly and allow it to play the game. And rather than being stuck in that little hole in queue space where it can't figure out anything because it has no idea how to do the basics of the game, Instead, it knows enough that it can actually explore and start getting better on its own. So that's my idea for one way to make reinforcement learning a heck of a lot more useful. I don't know how far it is in the literature, but I think it could be really useful. Last is kind of a far out topic, which I don't even have a really great solution for, but it's evolving communication. Let's say you have two of these reinforcement learning AIs that are trying to learn how to do things in an environment, trying to learn how to win the game. How can you get it so that they are able to send information to each other, and more importantly, realize that that communication actually means something? So let's say we have two Roomba AIs, and one of them is trying to get the blue ball over here, and the other one's trying to get the red ball over there. It would be useful if they could communicate with each other using, say, lights on their head or something like that, saying, oh, I'm going left, so please stay out of the way, I'm going to go that direction, you go around me. You know, traffic signals, that sort of thing. Well, intuitively, if you give that sort of output to an AI just straight, it will start doing random stuff, and it will be absolute noise. And because it's absolute noise, the other AI will say, that's complete noise, I have no idea why that would mean anything, so I'm just going to ignore it. So due to the fact that the other AI just ignores it, AI2 just ignores it, AI1 has no incentive when he's learning to try and do anything particular with that light, to try and communicate anything, because the other AI just ignores it. So you have this weird chicken and egg problem. So one thing that I was thinking might be interesting or useful is to start by having it so that the AIs have absolutely no control over what they're saying, but instead it's just taking that mental summary that they have of the world and posting it. It's like sticking your emotional state and all sorts of other information associated with you in a big sign on your forehead that anyone can just blow up and see. So someone else can say, oh, that dude's kind of angry, I should stay back from him. Which is great and all, in that it allows them to interact and potentially be able to cooperate and stuff like that based on their emotional state, but it doesn't really get the sort of high-level communication that we as humans want. So what I think would be really interesting is to take that summary, stick it on their forehead, have them play a game for a while with being able to say, oh, I'm looking at that summary, looks like that dude's angry, I guess I'll stay back here, or he gets angry every time I get near the red ball, and I don't care about the red ball, so I guess I'll stay away from it. And then, once they've learned to actually take that into account, start giving them the ability to lie. To say, oh, I'm going to pretend to be angry because I know that you always back away when I'm angry. Or maybe I don't have to actually be angry, but I can just flash that. And since they've hopefully already evolved to assign some significance to that communication, hopefully that will evolve from lying to a more meaningful dialogue. So, just one thought, certainly needs some work and some testing, but it's an idea. And I think an interesting problem. So that pretty much sums it up for this talk. Any final questions? All right, well, thank you.
Are slides available?
Yes, I will post them with the YouTube video.
Do you know who Ray Kurzweil is?
I've heard of him, but haven't read his works yet.
Okay, so he has a book out called The Singularity is Near. Was published in 2005. I just kind of looked up. I actually have the book and I've read most of it. But he goes into the whole concept of the singularity, and he's predicting the late 2030s or the early 2040s.
Yes, and if you asked me 5 years ago, I would have told you he was full of it, and we had no idea. Now I wouldn't say that.
So Kurzweil is of the technological singularity persuasion.
Yeah.
And he's specifically referring to AI singularity, which are completely different things.
Are they not?
Yeah, they're completely different.
How are they different?
So Kurzweil's argument is that if you take a graph of technology,
Right. Everything moves at an S curve.
then it's going like, you can look at, it's an exponential growth basically. And so then he extrapolates that to say,